Well, hello, Jacksonville. All you guys came out today. I just want to start by saying I wasn't going to start like this, but I want to start by saying that I was an undergrad at UNF as well. And we didn't have this when I was a student. And I cannot believe this community engagement here in Jacksonville tonight. It makes me feel so good that y'all love astronomy so much. So this is very exciting for me. Okay, great. So today I'm going to talk to you about black holes. It's going to be a little bit of story time about different stories about black holes. When I gave my abstract to the Astronomy Club, I gave them I made some bold claims. I told them that not only was I going to tell you what a black hole was, but I was going to say how it might help answer really deep questions about just the nature of reality as we know it. So let's see if that happens. Okay. But first, let's start with what a black hole is. So happily, there's this wonderful diagram that makes my life a lot easier to do this. So a black hole is an extremely dense, compact object. And at a certain point, it curves space-time so much and the gravitational pull is so strong that not even light can escape. Okay? That point is called the event horizon. So the event horizon is about here. It's kind of the boundary of the black hole. And this is the point of no return, as they say. Nothing can escape this point. Furthermore, at the center of a black hole, once you get inside, at the very center is something that we call a singularity. Now, a singularity, we're going to be talking about that a pretty decent amount today. So a singularity is a point of infinite density, infinite curvature, which is very hard to imagine. And we never get to see it because it's behind the horizon. On this diagram, those are the only two things that are actually associated with the black hole. However, there's a lot more going on. The rest of this diagram is normal matter that helps astronomers find where these black holes are, right? So what else do we have? So a black hole, its job in life is to attract the matter that's around it, right? You can think of it as being hungry. This is usually the sort of analogy that we have. And so this light, this matter, all around here forms what we call an accretion disk. Okay, so this accretion disk, it's made up of dust, charged particles, things like that. Okay, so this is the accretion disk. And all the while, it's spinning very quickly, super fast, like a fraction of the speed of light, quite close. Yes. Oh, yeah. Yes. Okay. Yes. Yeah. Good. Okay. Great. Yeah. Let me know about technical difficulties. I'm a theoretical physicist, so sometimes I don't catch on. Yeah. Very good. Okay. So we have this charged matter, and in physics, we know that when charged matter is moving around, it creates radiation. So this charged matter in the accretion disk is shining bright. And that's what lets us be able to identify where these black holes are. Because if it wasn't for this, let's be honest, we couldn't see it, right? That's the sort of whole deal with black holes. And so what else is on this? So because this matter is spinning around, this charged matter, it also creates magnetic fields. And so the magnetic field is, at least the most common theory, is that these jets are caused by the magnetic fields. So some matter is just always going around here. some matter falls into the black hole, but some matter follows these magnetic fields that are being created by the spinning atom. Okay, so these are called relativistic jets. So there are three things that can happen. The matter can spin around the black hole in the accretion disk, it can fall inside, or it can get projected out into a relativistic jet. Okay. And this photosphere is just very close to the black hole. This is where the matter emits the most radiation. So it's this bright ring that's around the black hole. And there's an innermost stable orbit where matter can be safe from never falling into the black hole. So maybe you're out here, matter won't fall in. But then as soon as it gets inside, matter will fall in. And then once it falls in, of course, there's no escape. Okay. So this is basically the diagram of what a black hole is. Now, not only do we have these diagrams, remarkably, in the last few years, we can even take a picture. Okay, that's how awesome we human beings are. Okay, so here are actual photographs, actual images that we have taken of two known black holes. All right, so one of them, Sagittarius A, this is the black hole that is at the center of our Milky Way. I'm sorry, Sagittarius A star is what it's called. So it exists, it's called that for two reasons. Because it exists near the boundary of the Sagittarius constellation. I just found out in preparing for this very presentation why the asterisk is in the name. And it's very funny. So in physics, when we shine light on an atom, it goes into a higher energy state, and we refer to that as an excited state. It doesn't mean that it's happy, it's just the word we use. And in the old lingo, I guess, they put an asterisk to show that an atom was in the excited state. So it turns out that the astronomy community thought that this was such an exciting discovery that they added this asterisk to the name. I thought that was really funny. And as you can see, these pictures weren't taken very long ago at all. We finally achieved this only in 2019. So that's interesting. So there are two. So M87 star. This is the one in the Messier 87 galaxy. So it's a bit further away. It's interesting that the black hole that's further away, it looks like the picture is clearer than the black hole in our own galaxy. Why do you think that is? I like both of those answers. I like tilt a little bit more because in our own galaxy, so the way our galaxy works is that it's a plane, right? It's a disk, and the black hole is at the center that we want to see, but we are inside the disk. So we have to cut through all of that, all those stars, all that matter. We've got to cut through to see the black hole. Whereas the one far away, we just can look at it. Yeah. Well, it does, right? So how do black holes form? They form because matter falls in, matter of all kinds. Could be dark matter, could be regular matter. Matter of all kinds gets to a point where it's so dense that a black hole is formed, right? So dark matter probably does play a role. The Higgs boson plays a very important role in mass in general, but not the black hole one. That one plays a role in the mass of only like little particles. Yeah, great question. Wow. From the mouths of babes, right? Okay, now let's learn a little bit about the Milky Way's biggest celebrity. So its name is Sagittarius A star, occupation black hole. Its distance is about 2 billion astronomical units. So an astronomical unit is the distance from the Earth to the sun. So it's about 2 billion of those. The mass, about just 4 million times the mass of the sun. Furthermore, it's spinning. The black holes that we actually observe in the universe, they all seem to spin. Some a little bit, some more. So this is spinning, and there's a maximum amount that they're allowed to spin, theoretically. And ours is spinning at about a little over 10% of the maximum that it's allowed to spin. They move. Yeah. Because the galaxies move, they move also. Yeah. Okay. Very good. Okay. Now, I'm wondering, so does anybody happen to have any guess or ideas as to how black holes were discovered in the first place? Accident. But if somebody fell in, they could never tell us. So this is a very good question. I kind of did a trick question on you guys. So they were discovered first, theoretically, right? So all it took was good old pencil and paper. So this happened back in 1915. And so how did that work? I'm going to actually show you a little bit about that. Let's see if it's super traumatizing. So here is an equation. This is an equation, and this equation has two different solutions. It can be solved if x is equal to +1, or it can be solved if x is equal to -1. Very similarly, a black hole is also the solution to a particular equation. And that's why this man is so famous. So this man came up with an equation. This is Albert Einstein. He came up with his Einstein equation. And this equation here tells you, the solutions tell you what sort of space-times are allowed in our universe. It would take me between 3 months and 10 years, I see some babies here, to explain this equation to you. So we will not do this. But I wanted to give you an idea of where black holes came from. Okay? So the solutions to this equation, there are many solutions. So just like this, there are different solutions. In this case, there are many. And they get kind of crazy. So one of the solutions is like the expanding universe that we live in, and this expanding universe is a solution. A negatively curved universe is a solution that actually turns out to be very important, but not for this talk. Wormhole and the black hole. Well, the black hole is a solution. Not only that, it turned out that this is the very first solution that was ever found of this equation. It was found by this man, Karl Schwarzschild, the German physicist. He found the solution the very same year that the equation was written down by Einstein in the first place. So he works, sometimes you have to work very fast in physics or you'll get scooped. It's like being a journalist. You have to just, as soon as something new comes out, you have to just do a calculation right away. So this is so interesting. I wonder if we have any German speakers here. Does anybody know, can anybody tell us, does anybody happen to know what the word Schwarzschild might mean in German? It means black shield. This is just that guy's name. That he happened to find. He didn't do anything special. He just imposed spherical symmetry, and that's it. The solution that he happened to find is none other than a black shield. I find that extremely bizarre, okay? I find that Extremely bizarre. Yes. So a black shield, what does it shield? It shields the singularity that's inside, right? We thought that there was a singularity there. So that kinds of brings us to our first secret that black holes are maybe telling us about reality. And this is what I'm about to describe is called cosmic censorship. So here's the idea behind cosmic censorship. So the concept of infinity, we know what the word infinity means. The concept of infinity actually crops out all the time in our lives. For example, if I ask you how many points are contained in this sphere, well, there's an infinite number of points in this, cylinder. There's an infinite number of points in this cylinder, okay? Because the size of a point is 0. So there's infinite in there. If I ask you how big the universe is, it's infinite. Probably. There are other theories. We don't need to get into all that. Okay, it's probably infinite. However, seems to conspire so that we do not see those, that we do not experience those infinities. For example, even though there are infinitely many points, we can't see that infinity because quantum theory tells us that we can only measure like a certain distance. Like we can't go below that distance yet, maybe ever. Okay. So we're not allowed, we don't see that one. We don't see this one either for a completely different reason. Even though the universe is infinite, the speed of light, the way the information reaches our eye, that's finite, right? So we can only ever see a certain distance out. We will never be able to see. This is not allowed. Okay. What's the big deal? We'll just cook up faster than light travel. We'll just get better tools. And then maybe we'll be okay. Then fair enough. Okay. Then along comes a black hole, right? Along comes this solution. And like I say, this solution didn't have to be the way it is. However, finally, when we get a chance to see an infinity, to see a point of infinite density and curvature, the universe makes this very mysterious horizon so that we cannot ever see it. This is weird to me. And so this is called cosmic censorship, and people think about, I wonder what is it about reality that makes the world like this? So can never escape now. I can't. I guess I'm proof. I'm back here now. So maybe you're right. Okay. So now here's another secret of black holes: gravitational waves. It's no secret that black holes produce gravitational waves. Even my arm passing through the air produces gravitational waves. It's just not massive enough, not yet, that you will be able to detect them. Okay, we'll see. What is a little bit secret in this concept of gravitational waves from black holes is that these gravitational waves, they turn out to tell us interesting things about gravity and maybe how we can unify it with quantum mechanics, believe it or not. But let's start slow. So let's first talk about what gravitational waves are. So for example, the gravitational waves I'm talking about are from, for example, 2 inspiraling black holes. Okay, so this is called a black hole binary system. Oh, I think the thing is gone, but that's okay. I was going to probably blind somebody anyways. Okay, so we have 2 inspiraling black holes here, and these produce gravitational waves. Again, not so long ago, the LIGO and Virgo collaborations were able to actually record and measure these gravitational waves for the first time. Okay. In another very bizarre coincidence, the frequency of the gravitational waves they measured happened to be, if you translate them to sound waves, it happens to be within the frequency of human hearing. That's very bizarre. So you can look it up, you can and listen to them. You can listen to the gravitational waves that they measured. Okay, it's very strange. It didn't have to be like that. Okay, and so the part that I was talking about for quantum field theory coming together with gravity, we're kind of interested in a very special part of these gravitational waves. So this diagram shows the different phases. So at first, two black holes are in spiraling, right? Then they finally merge here, and then they come together and form just one black hole, right? And then you just have this normal, bigger black hole, okay? This merger is what we're interested in. And this is this little ring down phase. These waves are called quasi-normal. This is just what they're called. That's not very important. However, it's interesting from a theoretical standpoint, because if we're wanting to study quantum effects or quantum corrections to gravity, what we do is we start with a black hole, and we want to study like small perturbations to that geometry, small corrections away. And if we look at the figure, that's kind of exactly what the merger phase is, right? It's two separate black holes coming together, then they merge and they're almost one, but there's still that perturbation there. And then finally they form just a regular black hole. So you can learn a little bit about perturbations away from regular black holes by studying. So this is one of the secrets that maybe black holes have in store for us. Okay. So similarly to what I've just said, it turns out that these gravitational waves that I just described are kind of like the music of space-time, or space jams, if you like. Yeah, that was very kind. Thank you for laughing. So proud of that joke. Okay. Now, what do I mean? So the music of space-time. So let's first forget about black holes just for this slide, and let's consider the classic question: can you hear the shape of a drum? Can you hear the shape of a drum? What does this question mean? On one hand, if I give you a drum and you start playing this drum, a good musician can tell the sound, right? They will be able to tell the frequencies, etc. Okay, the good ear. The opposite end of that is, if I give you the music, if I give you the frequencies of the sound, can you give me the shape of this drum? I'm not talking about, is it a snare drum or is it a bass drum? I'm talking about, is it round, is it square, is it a triangle? Okay. The answer to, and this question, it's a math question. However, there's no equation, so it's okay. The answer to this question turns out to be sometimes. Yeah, it took the community 30 years to answer this question, by the way. It's not that easy. But if you're dealing with like a drum that is very symmetric, like a normal round one, right? If I hear music coming from a round drum, I can say, yeah, I can tell that that's round. But, there are some crazy counterexamples like this that were cooked up by this group impressively, but, the very extreme counterexamples where if I heard the notes, I couldn't tell whether it was coming from which one of these crazy looking drums. Okay. What does this have to do with black holes? There's a version of this question, can you hear the shape of a drum for black holes, as well? That version is called, can you hear the shape of space-time? Okay? So the music, yet again, is like the quasi-normal modes are like music. right? The gravitational waves. And it turns out that if you study these, they can be used to diagnose what sort of space-time or universe you're in. For example, it could tell you if we're in the expanding universe like we are, or if we were in a negatively curved universe, which we're not, or even if there are more than 4 space-time dimensions. We're used to 3 spatial dimensions in one time, right? But if there are more than that, as predicted by string theory, gravitational waves can tell us something about eventually. So this is a secret that they might have in store. Another secret that's kind of been let out of the bag in the 1960s is that black holes, they actually have a temperature associated with them. So they have a temperature and it's inversely proportional to the mass. So the bigger the black hole, the colder it will be. Okay? The fact that black holes have a temperature has had incredible consequences. So one thing is that, and this argument is due to Stephen Hawking. One thing is that if something has a temperature, it radiates. Everything with a temperature gives off radiation. This is kind of a rule, right? And so here's how this works for black holes. So how Hawking radiation works for black holes is, you can imagine this is a sort of toy description, this picture, sort of toy description of how it works. So in space-time, there are these virtual particles, as they're called. So a particle-antiparticle pair, space-time can be totally empty. Then all of a sudden, out of totally empty space, particle and antiparticle pair are created. But then they annihilate immediately, so we never see them. So I like to think of space-time as kind of like a bubbling soup in a way, where it's not so empty. There are these particle-antiparticle pairs that are created. What happens when you're super close to like the horizon of a black hole? It can happen that you're just at that special spot where one of the particles that was created falls in and the other does not. This can happen. And this is the sort of model for how Hawking radiation is a thing. Things that have temperature, things that radiate. This got physicists very excited because we learned a lot just from straight up black body radiation. A black body is just like a perfect emitter, and it emits radiation over all frequencies. And the shape of that curve allowed us to begin the journey towards developing quantum mechanics. Okay? So there was, and just like that, the fact that black holes have a temperature, they have managed to teach us a great deal about the quantum nature of gravity. Although, of course, there's still a lot of work to be done. We don't have, tell me. That was really good. Give me 5. That was a good one. Okay. Very good. That's what I like to hear. Okay. So, weirdest secret of all. When I told you that black holes can tell us things, that when I made you this argument that black holes, because they're thermal, they can tell us about quantum gravity, what exactly do they tell us? Black holes turn out to be like holograms. Okay, so a hologram, as we're familiar with from, say, Star Wars, it's a 3-dimensional image. So Princess Leia here is a 3-dimensional image. However, she's projected and stored on a 2-dimensional surface. So inside R2 here, is a two-dimensional surface, right? He's probably got a two-dimensional surface on his little eye here. Light is shining through. Everything about that image is on the two-dimensional surface, but it projects to three dimensions. This is what a hologram is. It turns out that black holes are also like holograms because all of the information that describes what the number of states, quantum states they might be in, lives on the boundary. So temperature also implies that there's a quantity called entropy, which I've just called S. And this measures, like I say, how many quantum states are available. And it turns out that the number of states available goes like area, where everything else that we know and love, it scales like the volume instead, right? If I want to know everything about this table, if I want to know all the information that's in it, what would I do? I would just like saw through the table slice by slice, and I'd have to look through the whole volume to understand this table. The black hole, no. All of the information, all of such information is at the horizon only. So this is why it is like a hologram. This is called the holographic principle, and it has led to advances that are beyond the scope of this talk that I would love to give. I'd love to talk about at some point, but that's sort of the research that I do and many people do in theoretical physics is studying this. Right. And I will say one last sentence about this. So there is potentially, why would it go like area? Well, entropy, there is also something called entanglement entropy. So if you take two particles, their state, and they're created like this, the state of each particle depends on the other. And so they're forever entangled. So maybe the fact that the entropy of a black hole is like this is because all of these particles are getting created on the perimeter, on the outside area. And so maybe it's related to this thing called the entanglement, quantum entanglement of these particles that are being. So this is possible. We don't know. And that's it. Thank you very much.